What does under relaxation mean? Under relaxation means this. So Jacobi has a ek plus 1 equal to r times ek, right? R is the iteration matrix that has the eigenvalues like that. So under relaxation, this is Jacobi. Under relaxed Jacobi wants to have a solution area that looks like this. Looks like lambda times r plus 1 minus lambda times I times ek, where lambda ranges between 0 and 1. Okay. Do we know what effect does taking average between a matrix and an identity have on the eigenvalue and eigenvectors of the matrix? What happens if I take an average, a weighted average between a matrix and an identity? What happens to the eigenvectors? Maybe I shouldn't use lambda. Lambda usually I use as eigenvectors. So let me say gamma. Okay, gamma. Okay. So if Rx equal to lambda x is an eigenvector. Is that still an eigenvector of a weighted average between R and identity? Yes. What happens to the eigenvalues? It's the same as the weighted average of the eigenvalue and 1, right? It's gamma times lambda plus 1 minus gamma. Okay, now remember in the iteration matrix of the Poisson's equation using Jacobi, my lambda ranges from minus 1 to 1. It ranges from slightly greater than minus 1 to slightly less than 1. Okay, or if I write it, if I plot it on the real axis, I don't need this. If I plot it on the real axis, minus 1, 1, it ranges from here to here. So this is my lambdas. Now if I use a different color to indicate this weighted average, where would 1 be mapped? So if this is gamma, let's use 0.5. Let's say gamma equal to 0.5. So this is halfway between gamma and lambda and 1. Where is this mapped to? Where is 1 mapped to? 1 is mapped back to 1, right? 1 plus 1 over 2 is equal to 1. Where is minus 1 mapped to? It's mapped to 0. So everything here is linearly mapped into a smaller range that lies between 0 and 1. Okay? And what if I choose a slightly different lambda? What I use a lambda equal to 0.3, for example. This is gamma plus 1 minus gamma divided by, oh, that's fine. There is no. What if gamma is equal to 0.3?
The range becomes smaller.
The range becomes smaller, right? So 1 is always still mapped to 1. And minus 1 in this case is mapped to something even closer to 1. And if gamma is closer to 1, then I'm going to be mapped into a wider range. But no matter what the case is, under relaxation it has the effect of mapping something that is close to minus 1 away from minus 1. Right? It is still going to map something close to 1 to something close to 1, actually even closer to 1. But I already got rid of by doing the under relaxation, I got rid of the slowly decaying mode that is not smooth. So by doing an under relaxed Jacobi, I can make sure no matter what happens to the initial solution error, I'm going to get a solution error that is smooth after many iterations. So what is under relaxed Jacobi? How do I achieve an error equation like this? Well, actually very simple. Very, very simple. So instead of doing xk plus 1 is equal to minus d inverse L plus U times not L, let me say B minus L plus U times xk, the under relaxed Jacobi performs a linear combination and averaging between this and the original xk. So I'm doing xk plus 1 is equal to minus gamma times the same guy plus 1 minus gamma times xk. Alright, okay, so with this iteration, you can still verify that if xk is the exact solution, xk plus 1 is also the exact solution, right? Because I'm taking linear combinations of the exact solution and still get the exact solution. The linear combination coefficients are gamma and 1 minus gamma, right? Question?
Just to clarify, is it minus 1 minus gamma xk or plus?
It's plus. It's 1 minus gamma times xk. Xk. So this part is the Jacobi iteration, right? This is the Jacobi iteration times gamma. This is 1 minus gamma times the original solution. So if I go to MATLAB, doing Jacobi iteration is U equal to Jacobi U and B, right? This is Jacobi iteration. Can somebody tell me how can I do a under relaxed Jacobi iteration?
Gamma.
It's equal to gamma, let's say 0.5 times Jacobi, then plus 0.5 times U. That's under relaxed Jacobi. What if my gamma is equal to 0.8? This would be 0.8. And what is this? 0.2, exactly. I'm taking the averaging, weighted averaging between the Jacobi iteration and the previous solution value. That's on the relaxed Jacobi. And that makes sure my solution error is going to be smooth no matter what the initial solution error is. Okay, any questions on the relaxed Jacobi? That is the first component in the multigrid. Yes?
So quick question, so go back to the slides.
The slides here.
Yeah, so here we have a gamma D inverse with a parenthesis, like there's a B minus LU.
Yes, okay, so make sure this is here, not gamma times
That's right.
D inverse. Yeah, okay.
Yeah, so my question is, can we take the B out of the parenthesis because it won't change the error function at all?
Can we take the B out of the parenthesis? Sorry, can you?
Oh, so can we just do a D inverse times B out of the bracket? Because that's a constant part.
Oh, that's a constant part. You mean that is a part that you can pre-compute?
Yeah.
That's right. You can do that. Yes. Good point. Any other questions? Yes.
So if this under relaxation is mapping things closer to 1, in the slow mode, that smooth is going to decay even slower, right?
That's very good point. The part that is decaying slowly is going to be decay even slower because the something close to 1 is going to map to something even closer to 1. That's exactly right.
So the trade-off of having a smooth error is better than having something that's oscillating a lot and decaying fast.
That's true only if you use multigrid. We are going to see that in multigrid, the smooth part of the error is going to be dealt with by the coarse grid. So on the under-relaxed Jacobi iteration, the responsibility is totally trying to decrease the oscillatory part of the error. Right? That's a very good point. So the smooth part of the error, you can deal with it on the coarser grid. And that is going to be much cheaper, much more efficient than trying to deal with the smooth part of the error on the fine grid. Any other questions? Do you have a question? No? Okay. Okay, so let's go to MATLAB and the multigrid operation 1 is smoother, so let's start putting that into MATLAB, and then we take a break. So I'm going to construct a function called multigrid. Multigrid is also an iterative method. So the input and output is going to be exactly the same. U next is going to be the same as the Jacobi iteration. So if you call the multigrid function, it completes what we call one cycle of multigrid. The first task in this cycle is to do an under-relaxed Jacobi iteration. So I'm going to copy this, paste onto here. Okay, and so in order for me to do this, oh yeah, that's good enough. And because I want the solution error to be smooth, it's usually not sufficient to do just one iteration. So here, let me do 5 iterations. All right. So that completes the first part of multigrid iteration. This is called the pre-smoothing. We are also going to be doing a post-smoothing. We are going to code up later. But the next thing after the pre-smoothing is solve the error equation on the coarser grid. Okay, so let's take a 5 minutes break and then start to discuss what is the error equation. All right.